Good afternoon and welcome to the Winter 2022 live stream from the Science Oxford Centre. My name is Daniel and I will be your host today here in the classroom at the Science Centre, where we have got lots of fantastic demonstrations and experiments to show you all about weather. I could not do this by myself though, of course, so I've got Alicia today helping me out. She will be helping set up, clear away and run some of our experiments. And we've also got Sean and Sarah running some of our tech support, making sure that we can stream directly to you in your classrooms. Thank you so much for joining us today. We are really excited to have you here. And I can see that many people are saying hello from the schools. That's great. Please do keep using the live chat throughout the show. We'll ask questions throughout the show and sometimes give you a couple of minutes to discuss those answers in your classrooms. And teachers, it would be great if you could submit some of those answers into the live chat so that we can discuss them on the live stream. At the beginning, before we started, we had a question up asking, where do clouds come from? And we've seen lots of answers coming in. So Aqua class think they come from water vapor, which is a fantastic suggestion there. Thank you very much. And lots of people are talking about them being made from water. So Maxim, thank you very much. I know a few people also mentioned the water cycle specifically. This is great knowledge. Thank you very much. And you're absolutely right. Clouds do come from water. So lots of sources of water around the world, lakes, the ocean, puddles and ponds, all have got water in them. And sometimes that water gets enough energy that some of the water particles evaporate into the air. So evaporation is the process of a liquid turning into a gas, and those water particles become water vapor in the air all around us. And there's water vapor in the air around us right now. It's an invisible gas. We can't see it, but it's there. And that water vapor, when it's in the air, will sometimes get carried up by the warmth because heat rises. So as the air gets warmed up, maybe because the sun is shining on the ground or we've got heating on in the buildings, that heats up the air above it as well. That heat carries the water vapor up higher into the air. And we can see heat rising in lots of different places. You might have seen steam coming out of a kettle or smoke from a fire, those hot things rising up. And I'm going to show you a quick demonstration now so we can definitely see that heat does rise up as well. So over here, I have got some tea bags, and I love a good cup of tea. But for this experiment today, I'm not going to be drinking the tea. In fact, I don't even need the tea at all. The thing I'm interested in is the tea bag. So what I'm going to do is I'm going to cut the top of this tea bag open like so, very carefully, nice and straight along the top. And I'm just going to get rid of all that tea, which seems like a waste, but maybe I can boil that later. And then what I'm left with is this thin, papery material with a lovely column of air through the middle of it. And I'm going to stand that up on its end. And I'm going to try and heat up the air inside that column and hopefully give it enough warmth that it will lift the tea bag off the table. And I'm going to do that by setting fire to it. So I'm going to set fire to the top of this papery material. We can watch it burn away, and that fire now is heating up the air inside the column there, and it's lifting up and up, and it has enough momentum to carry with it the ash burn away from that tea bag there. So I can see that's up in the air now, and we might see it come back down in a second. Just in case you missed it, I will do another one. So I've got another tea bag. Oh, there we go. And again, I don't really care about the tea inside, so I'm going to cut it open straight across the top. There we go. Empty all that tea out. And that will leave us with this column of air inside the tube there. And when I set fire to it, it will heat up the air inside. And the tea bag, as it's burning away to ash, is getting lighter and lighter until eventually the air has enough upward force to lift it into the air. Fantastic. And away it goes. So just like that tea bag, when the air gets warm enough, it can lift that water vapor up into the sky. And as it gets higher and higher, the temperature starts to drop because there's less air pressure the higher you go, and pressure and temperature are related. So if the pressure decreases, the temperature decreases. And as the temperature drops, water vapor temperature drops as well. And that means it can condense back into a liquid form. So water vapor, a gas, gets colder and it condenses into water droplets. And you've probably seen Sensation on a glass or on a window. If you've ever breathed onto a window and made it foggy on there, that's the water vapor in your breath getting very cold on the glass suddenly, so it turns back into a liquid, and we can see those droplets. The droplets that make up a cloud are probably 100 times smaller than a millimeter. But when there are millions of them all together, we can see them as clouds. And I'm going to try and make a cloud here in the classroom today. In fact, I'm going to try and make a cloud inside this bottle. So in this bottle, I have a liquid. Okay, so a very small amount of liquid, and I'm going to shake it around to try and get as much of that liquid to evaporate as I can. Okay, so I've got lots of vapor now in this bottle. And I'm going to ask my associate Alicia here to come and give me a hand with this, because I need two hands for this. So I've got my lovely evaporated water vapor in there, and we're going to increase the pressure in here, because if we increase the pressure, we're going to increase the temperature. So if you can give that a few pumps there for me, Alicia, thank you very much. And I can feel this is getting nice and firm. The pressure is really pushing out, and that water vapor is under a lot of pressure. And in a moment, I'm going to take the top off of this, and the pressure is going to very suddenly drop, which means the temperature is going to very suddenly drop. And that means that that water vapor should condense back into water droplets. And in fact, you can probably see the cloud is sort of leaking out of the bottle there as I give it a bit of a squeeze. But let's trap it back in again, because I don't want it to go away entirely just yet. So keep your eyes on that cloud, and as we add more pressure again, we can watch that liquid water droplet evaporate back into water vapor, going invisible again, because the pressure is increasing, the temperature is increasing, so it evaporates. And when I release the pressure, it drops, which means the temperature drops, which means that water vapor condenses back into lots of little water droplets, creating a cloud in a bottle. Isn't that fantastic? Amazing. Now, I'm going to trap my cloud in there for later. But what happens to clouds after they've formed? Well, all the little water droplets in the cloud, they move around, they bump into each other, and they collect and they get bigger. And then two bigger ones become an even bigger one. And when they get big enough, the warm air pushing them up isn't enough to keep them in the air anymore, and gravity pulls them back down as raindrops. And sometimes, you might have noticed, after rain, we sometimes see something very colorful in the sky. I'm sure you know I'm talking about rainbows. But I want you now to spend a few moments talking with the people in your class about what you know about rainbows. So what are the colors of a rainbow? What makes a rainbow? How do we see them? Have a quick chat with your people in your class. We'll give you a few minutes, put your answers in the live chat, and then we'll come back and share them. Hello and welcome back. I hope you had some time there to discuss with the people in your class what you know about rainbows. So let's take a look at some of your comments. So Dabs had said that red, orange, yellow, green, blue, indigo, and violet are the colors of the rainbow. Fantastic. You're absolutely right. And Sapphire thinks it is light going through water droplets and making the light split. That's a lovely definition, a lovely explanation of how rainbows work. And there is also gold at the end of the rainbow. That is an interesting idea. We do have a small pot of gold over there, but I'm not sure you'd find one at the end of every rainbow. And have we got some more comments there? The sun reflects off the raindrops, says Lily. That's a really good explanation there as well. Thank you very much, Lily, for that. And let's see, have we got one more? So when the rain comes and the sun comes up, the colors of the sun reflect into the rain. Brilliant. So you've got these same kind of ideas. Fantastic. Thank you very much for sharing that. And yeah, I think you're absolutely on the right lines. We know that we need sunlight to see the rainbow, and we need it to have been raining as well. The way that we see a rainbow is when the sun's light enters the water droplets left in the air after the rain, it gets reflected inside and it gets split up into the different colors. So the sun, the light from the sun is known as white light, and white light is built up of all of the colors of the rainbow. We've created the effect in the classroom here, not with rain and the sun, but with a bright white light and a scientific piece of equipment called a prism. So this prism here works in the same way as a raindrop. The sunlight will enter it from one side, or the bright light in this case, and it will get bent inside, splitting it up because the different colors get split up as they come out. And we've got a video, actually, we'll show you of how ours is set up. So we can cut to that now. So there is the glass prism, and you saw a flash of color there. But as we pull back and we go through from higher to lower, you can see the different colors of the rainbow shining through the prism. And if I go back up from the bottom, all the way back up to the red at the top there. Fantastic. And that's how we got this wonderful image behind me here. Now, we can also not just split white light up into different colors, but we can also play around with different colors of light to recreate white light. So if we get over here, for example, I've got some different torches that I made up. These are just regular torches with some filter paper over the top. So here you can see I've got some green filter over a light bulb, which means that that filter will stop all of the light coming through, and it will only allow the green color light to shine through it. I've also got a blue one, and I've got a red one, which will allow only those colors to shine through as well. So I've got my red, green, and blue torches. Now, when you're thinking about playing around with colors, mixing colors in painting, for example, you might think of your primary colors as red, yellow, and blue. And you'd be right for mixing things like paint. But when we mix colors using light like this, our primary colors are red, green, and blue. And just like when you're mixing paints, you can get secondary colors. So too can I do that with my torches here. So for example, if I take my blue and my red torch and I mix them together, what color do you think we will see? I'm going to cross them over now and we'll find out. So my blue and my red torch give us this color known as magenta. It's a purplish color, but it's called magenta. It's quite beautiful, actually. What if I was to swap out my blue for green? What color do you think I'd get if I mixed green light with red light? Well, I can show you that we get yellow light. I wonder who could have predicted that correctly. So green and red make yellow when we're mixing lights, which is quite different to the paint. And one last one here. I've got my blue light and I've got my green light. But what color will I get when I mix the two together? Have a guess. So we get this color called cyan. So cyan is sort of a bluey greeny color, neither of the blue or the green, somewhere in between. And we call it cyan. Now, as well, I said we could mix these three colors together. And if I do that, it should give us in the middle there, white light. So this section here, where all of the colors are shining together, gives us white light. Fantastic. And it's not just colored lights that we can play around with either. We can also make colored shadows. So if I introduce something here to block some of that light, there we go. You can see there I've got a black shadow on a green background. okay? Because the green light is being blocked, it can't reach there. So we've got green light on the wall and a black shadow where the green light can't reach. But if I bring in my red torch as well, and we get that yellow background, suddenly you can see that actually I've got a red shadow and a green shadow. So this shadow here, the red one, is formed where the red light can still shine to it, but the green light is blocked. So the red light is illuminating the shadow from the green torch. And over here, we've got a green shadow because the red light is being blocked by this thing here, but the green light is still shining. So we get a green shadow there as well. And we get the yellow in the middle because both colors are hitting that same spot together. And if I change it up and I take out my red torch and I add my blue, you can see there that we've got a green shadow and a blue shadow on a cyan background, because that's the color we get when we mix those two. And finally, if I swap out my green torch for my red, we can see that we can get a red shadow and a blue shadow on that magenta background. Fantastic stuff. Now, these torches are just white torches with some sort of filter paper over them, and I've created this thing here, which is all three of them stuck together. So I should get a lovely white color, but they're not exactly in alignment with each other. So I'm going to move these aside and shine this at the shadow maker there. And if I bring it closer, we should see that we can also get all of those colors as shadows at the same time. So this circle over here is the area where the green light is being blocked. So the red light still shows through and the blue light still shows through. And here blue and red come together to make magenta, but no green light can reach here because it's blocking the green light. And over there, we've got the green light where it's getting through. And over here, we've got cyan, where the green and the blue mix, but the red light can't get. And all around it, we've got the white light where all three of them are hitting together. And in the middle, where none of the lights are hitting, we've got the black shadow. So that's just something you can play around with yourselves. If you can get some expensive colored torches, or you can do what I did, make your own, just take some torches and put some sort of filter paper over them. You can use old sweet wrappers. There's lots of sweet wrappers going around. And Alicia, have you got a tin of sweets that we might be able to use for this kind of thing? So at this time of year, I usually have this kind of tin of sweets. What happened there?
I don't know.
You put that down on there and it seemed to roll up the ramp. How did you make it do that? So if I leave it there and I let go, it rolls up. How on earth did you do that? Have you guys got any idea? Have a quick chat with the people around you. Why did the tin roll up the slope? Put your answers in the live chat and we'll come back to you in a few minutes. Hello and welcome back. Right, let's try and solve this mystery then. How do you think that tin was rolling up the slope? I can see that Cook class have said magnets. Thank you very much for sharing that idea. I think it could definitely be magnets. That's possibly one way of doing it. Gavin Jones has said that there might be movement of water in an odd shape inside it. Interesting. So perhaps there's water inside and that causes it to move around, moving it up the slope. Interesting. Sapphire class have lots of ideas. They think maybe it could be magnets. It could be an optical illusion. Could be air pressure or anti-gravity. Those are some fantastic ideas. And I would challenge any of you to try to make something that works just the same way as this and see if you can make it even better than ours. But for now, I'm actually not going to tell you the mystery of the Rosa's tin. So I'm going to give that back to you, Alicia. You can keep that mystery to yourselves because I want you to keep thinking about that. But I will show you the way in which we can make something else roll up this ramp without touching it, okay? So I'm going to place this Diet Coke can at the bottom of this ramp here, and I'm going to try and move it up the ramp without touching it using a couple of different weather-based techniques. So one simple way I could move it up is with the power of wind. So if I get down here and give it a quick, oh my goodness, a strong wind would easily blow that up the slope, so that's no problem there. But a more exciting way of doing it involves this rubber balloon. And I'm sure you've seen this kind of thing before. I'm going to give this rubber balloon a rub on my shirt, okay? And I'm going to generate a static charge, which is something that happens sometimes when you rub two different materials together. So, bear with me. Okay, I think that's got a good static charge on there now. So I'm going to see if I can use this to move the Diet Coke can without touching it. Hopefully you saw that. I will try and do it one more time just in case you did not. But the balloon is not touching the Diet Coke can, and it is making it roll up the ramp. And that is because the static charge that I gave this balloon attracts other objects, okay? And it attracted with such force that it can move the Diet Coke can. It can also attract to other surfaces like the wall and support its own weight with that attraction, okay? So there's no blue tack or tape involved in that, and that's how the other balloons are held up as well, just with static charge attracting them to that object. But it's not just attraction. Some static charges can also cause repulsion. They can cause things to be repelled from them, pushed away from them rather than pulled towards them. And this machine here is called a Van de Graaff generator. And this is exactly what that does. Inside this column, we've got a rubber belt that will spin around very fast, rubbing against some metal at the top of this dome, generating on the dome a really powerful static charge. These machines can be quite dangerous if not used correctly. Luckily, I've been trained in how to use it, so I know and I'll be safe. But there'll be an enormous static charge in this dome here, which will hopefully repel some of these objects that I'm going to place on top of it now. So I'm going to turn it on. I'm going to hold on to this metal ball for safety, and we shall see if it can repel the tin foil cases. There we go. So rather than attracting them like the balloon attracted the can, this charge repelled them, pushed them all away, and we've got them all over the floor. I've made an enormous mess in here. Now, sometimes when a static charge builds up in an object, if it doesn't have anything to attract or repel, the attraction or the repulsion will just get stronger. It will build a really strong static charge, and it will try to discharge. It will begin to let some of that static electricity jump from itself to another object. You might have had a static shock yourself at some point, where the materials in your clothes or your shoes have rubbed together, and you've gone to open a door or shake someone's hand, and you felt a static shock between you and the person. And it's exactly the same thing here. It looks like a little bit of electricity jumping through the air. And I'm going to show you that with this here. We're going to turn the lights down for a second, so it will show you a little bit clearer what a static discharge looks like. So you should hopefully see what looks like a bolt of electricity jumping between the dome and the silver ball in my hand there. And you can probably also hear that crackling, snapping sound as well. There we go. So that static charge discharging from one object to another is exactly the same as another type of weather phenomenon that you might be aware of that looks like an enormous bolt of electricity jumping through the air with a sound that follows it as well. Yes, I'm talking about lightning. That was a small bolt of lightning there, because lightning in storm clouds is generated in exactly the same way. Water that makes up the clouds gets pushed up with the heat from updrafts that send it to the top of the clouds, where in a storm cloud, they freeze very quickly and start to fall as hail. And then as the water is rising up and the hail is falling down, those two things rub together, just like the balloon on my shirt, just like the belt and the dome in this machine. And they generate this enormous static charge. And it needs to discharge to something. So eventually, the attraction will be so strong that it will discharge to either the ground or to another cloud. And we see that as a bolt of lightning. Okay, and you could probably hear the sound there as well that follows it. That's because the lightning, the path it takes through the air, gets incredibly hot, hotter than the surface of the sun in the case of lightning. And that means that the air expands incredibly rapidly, creating a shockwave, a sound boom through the air. And that's what we hear as thunder. Okay. Exciting stuff. So we have discussed today clouds. We've had a look at rainbows. We've just seen lightning here in the classroom as well, and we've heard thunder. But there are many other types of weather and meteorological phenomena which are really interesting and have an exciting scientific explanation. And if you've got any questions about weather in general or about the things you've seen in the show today, do please pop them in the live chat now, and we might be able to talk about them at the end, or just email us any questions you've got, and we'll try to get back to you. And don't forget that you can visit us here at the Science Centre if you want to see more demonstrations just like this, or we can come to you and visit you in school, and we can bring some equipment with us to show you the same kind of things, different things as well. Before we go today, though, I just want to say a quick thank you again to Alicia and Sean and Sarah for all their support in running this. I could not have done it without them. I want to say a big thank you to you for joining in and taking part as well. It's been great to have you here, and we hopefully will see you again at the next one. And just before we go, I'm going to leave you with one final question. So, how is snow made? I'm sure you've seen it in the recent days outside, but how is snow made? Have a quick chat with the people in your class, and I would love to hear some of your answers. And I will just say a very quick thank you as well to some of the schools who have joined us today. So thanks go to North Hinksey, Cropredy, Stoke Mandeville, Barton Park, Bryce Norton, All Saints, Hanborough Manor, Bampton, Garsington, Juniper Hill, Queensway, North Kidlington, Watlington, Sandhills, Grove, Jessica Rolfe, Monkston, St Nicholas, Pangbourne, St Finian's, John Henry Newman, Ulm, Tyndale, Lady Grove Park, and Hayden Manor. Thank you so much to all of you for joining. If I didn't call out your name, thank you as well for joining, and hopefully we will see you on the next one.